Hi, I will talk about my project for casting. The first component is for aerospace at high altitude, and I chose titanium 64, which is also titanium grade 5 for the material, and I use ceramic mold casting for this component because ceramic can withstand higher temperature than sand, and it is suitable for low or medium production, and it is also expandable. And the core, I also use ceramic as the material, and the benefit of using the core is that it can enable the intricacies and complexity of the shapes of the casting, and so it's more flexible, and also it can facilitate uniform cooling and reduce the likelihood of defects. And now I will talk about the casting process. First, I will use 3D printing to print a plastic pattern, and I will use a core box to make the ceramic core. I will use 3 cores and make them into an assembly, and then I will put the pattern inside the ceramic inside the flex, and then I take the then I will take the pattern out and then put the core inside the mold. And after the mold is being made, I will pour the melted titanium grade 5 through the pouring cup and through the sprue and the gate, and then after the melted titanium 64 reaches the open riser, we will wait for the solidification. And during the solidification, I used the directional solidification techniques with the cores and chills outside the open riser. They will increase the cooling rate and direct the heat flow and improve the strength of the casting. And after cooling, we will break the ceramic mold, and after that we will do the machining and heat treatment to strengthen the casting, and then we can have the final component. And the advantage of this design is that I use the directional solidification, which can direct the heat flow, and it will eliminate the defects better, and also it will improve the strength. And but the disadvantage of this design is that the ceramic might not withstand the high temperature of the melted titanium alloy, because the melting point of titanium is around 1700 degrees, and ceramic materials is the melting point is 2000 degrees, which is not too much more than the melting point of the titanium. And the modification for this is that we can produce a better ceramic material, which has a higher melting point. And during the solidification process, since we're using titanium 64, which is an alloy, so the freezing range will have different cooling rate, and the cast structure. In the cast structure, the random orientated grains will form in the chill zones near the mold walls, and also near the near the cores. And the segregation of alloy components will form inside the chill zones because of the different elements in the alloy. And the second component is the automotive components inside the Formula One cars, which requires endurance during high speed and aerodynamic process. And I will use the carbon fiber reinforced polymers as the material because of its high performance in strength to weight ratio and durability. And I will use die casting for this component because it has better dimensional accuracy, and it will enhance the mechanical material properties for the component. And during the die casting process, first we should prepare the carbon fiber and the resin, and then put them into the mold, and then we will squeeze the die to the carbon fiber resin reinforced polymer, and yes, and during this process the advantage is the die casting process will strengthen the casting, the mechanism of the casting, and will improve the precision and the wear resistance. So it's suitable for the Formula One car application. And the disadvantage is that the complex process for carbon fiber reinforced polymers might include more processes like curing, and also in the solidification stage, the carbon fiber reinforced polymer will have different process from the metals. And third, for the component in the marine environment and at deep depths, I will use the HY100 steel, which has high strength, toughness, and corrosion resistance. And I will use the sand casting process for this component. And first I will make the pattern, and with the dimensional allowances of the 1.5 to 2% shrinkage from the shrink rule, and this will compensate for the shrinkage. And then I will make the core with the core box, like the first component in aerospace, and then we'll make the mold, and after making the mold, we will put the melted H100 steel into the pouring cup, and until the melted metal reaches the blind riser and the live riser, we will wait for the solidification. And I implement the external chills are put outside of the blind riser to increase the cooling rate and direct the heat flow, and then after solidification and cooling, we will remove the mold, and we will do the machining and heat treatment to strengthen the steel and improve the mechanism of the casting. So the advantage of this design is it has a pattern that will consider the dimensional allowances, which will compensate for the inevitable shrinkage, and also it used the blind riser and live riser to compensate the shrinkage too, and these risers will make sure the solidification will occur to the extremist in the pattern. And and the disadvantage is that in this design there are sharp corners, and which will create the stress concentrations and cause shrinkage cavity. And during the solidification process, there will be increased cooling rate due to the external chills and core, and the random orientation grains will appear in the chill zones, and there will be segregation of the alloy components like the first component in the first design. So these are the three designs for casting design for the three components. Thank you.